So let's start with momentum wave functions. We had already said that the momentum operator is an Hermitian operator, so we can talk about its momentum kets. Let me straight away start from the three-dimensional notation. Whether you do one dimension or three dimension doesn't really change much. This is equal to P prime, no, P acting on the ket P. Their form in general, they will form a continuous spectrum of momentum values, not just one or two, but we will see cases in which the momentum can only take discrete values, but in general, they will be continuous. So we have this completeness relation. This should be the unit operator. Furthermore, we know we will define their normalization. So if you take the inner product of two, it will just give you a Dirac delta function. So if you start with any ket, then you can expand this in terms of these momentum eigenkets. This is what we call the momentum wave function. You will see various notations for that. Sometimes it will be the same notation with the position wave function, but instead of R you will have P. Sometimes you will have a different symbol, but basically it means the same thing. You have a ket alpha, you expand it in terms of the momentum eigenkets, and the expansion coefficients are what we call the momentum wave functions. Now the question is, how do you go from momentum wave functions to the coordinate wave functions? Now, if you remember our previous discussions, we had seen that if you want to change your basis, then you have this unitary operator, which we had defined as, let's say, alpha beta, summed over alpha I, beta I. So this was our unitary operator, and its matrix elements was alpha beta, which was responsible to go from one basis to the other basis, or one set of coefficients to the other set of coefficients. Now let's do it explicitly over here. Let's say we have this phi alpha of P, which is defined as the alpha inner product of the alpha state with the P alpha ket with the P ket. This is equal to P. Well, I can just write 1 over here. 1 multiplying anything is just equal to that thing. This is equal to P d cubed R alpha. This is equal to d cubed R P inner product of P and R. Well, this is just psi alpha of R. Now the question is, what is this thing over there? Well, you see, if you just compare it with our previous definition of the U and its corresponding matrix elements, it was just the inner product of the basis kets. Well, this is nothing but the inner product of our basis kets. So this is exactly the same. This is a matrix element of that unitary operator that we had defined before. Now let us try to calculate this one. Now, rather than this one, I would rather look at this one, if you don't mind. They are just a complex conjugate of one another. And I will look at this thing, this matrix element. Well, on one hand, I know that this P ket is an eigenket of the P operator. So this is equal to R, P multiplying with the P ket. Well, that P over there is just a collection It's just an ordinary vector, momentum vector, so I can just take it out. No, you see, in this line what I'm using is P operator acting on this P ket is just P multiplying this P ket. This is not an operator. This is an operator. This is an operator. This is not an operator. That the second P, the P in the middle of the expression is the eigenvalue of the P operator. So I can just take it out. On the other hand, let us look at exactly the same expression. Well, you see, here I have a ket. I know that it's an eigenket of the momentum operator, but just treat it as an arbitrary ket. It has its own wave function. So I'm acting on it with the P operator, so I get a new ket, and I'm looking at the position wave function of that new ket. But we know that what the momentum operator is in, let's say, position space, this is equal to h bar over I gradient acting on Rp. Well, let me write it in this form. This is what we had derived before for any alpha. Just take alpha is equal to P. Since this line over here is valid for any alpha, it should also be valid when I take alpha to be a momentum eigenket. So that tells me that our P operator alpha, or P, this is equal to h bar over I gradient of Rp, but I also know that this Rp is equal to P vector multiplying that Rp. The left-hand sides are the same, so should the right-hand sides be. So which tells me that h bar over I gradient acting on this Rp, this is equal to P multiplying Rp. Well, this is just a differential equation. If you call this one psi P of R, it's a differential. For each component, it's a partial differential equation. You can just solve it, and psi P of R is equal to e to the power I over h bar P multiplying R. Of course, there's some normalization constant. So this is the wave function of the momentum ket. We also know that P of R should be equal to n star e to the power I over h bar P dot R. Now let us try to determine what this n is. N is not arbitrary. N is fixed by our normalization conditions. You see P prime, the inner product of two momentum eigenkets. This should be a Dirac delta. But at the same time, I can write that as d cubed R, P prime R, RP. This should be equal to this Dirac delta. Well, I know both of the inner products on the left-hand side, so let me just substitute it. D cubed R. Well, P prime R is N star. Oops, sorry, here I have a minus sign. E to power minus I over H bar, P prime dot R. The second inner product in the integral is N times E to power I over H bar, P dot R. This is equal to D cubed R, N squared, E to power I over H bar, P minus P prime times R. This is equal to N squared. So do you know this integral? Let me write it in this way, e to power I k dot x, k times x. From minus infinity to infinity. Well, this is 2 pi times Dirac delta of k. Well, here instead of k, I have the change difference in p over h bar, so that integral just and I have three integrals, three position integrals, so it is 2 pi h bar cube times the three-dimensional Dirac delta of p minus p prime. And this should be equal to Dirac delta cube of p minus p prime. And so this tells me that the magnitude of n should be equal to 1 over 2 pi h bar to the power 3 halves. Well, the phase of n we cannot really determine, but it doesn't really matter. So you can just choose the phase of n to be 1. To be 0, to be 1, you can choose n to be a real number. So n is equal to 1 over 2 pi h bar cube square root. So now we know how to go from one wave function to the other wave function. You see psi alpha of r is equal to r alpha. This is equal to d cubed p r p p alpha. D cubed p, that inner product is nothing but 1 over 2 pi h bar to the power 3 halves, e to power I over h bar p dot r phi alpha of p. Or phi alpha of p, which we define as p alpha. This is equal to d cubed r p r r alpha. If you just use this matrix element over here with n, we had already evaluated it, it is d cubed r e to power minus I over h bar p dot r divided by 2 pi h bar to the power 3 halves of psi alpha of r. Well, you see these two relations are basically Fourier transform and inverse Fourier transform. So we didn't actually make explicit use of Fourier theorem, but nevertheless in our formalism it just automatically arises. Just a word of warning, we were discussing with your friend that we are talking about a single Hilbert space. And in this single Hilbert space, you are basically free to choose your basis. Just like in real space, you are free to choose your directions. But since you can choose one among infinitely many bases, doesn't mean you are talking about different space. You are talking about the same space and the same ket. Of course, you can choose one basis and then prefer to represent your ket in terms of the expansion coefficients in that basis, or you can choose a different basis and you can hence choose to represent your same ket using the expansion coefficients in this different basis. Of course, the expansion coefficients will look different, nevertheless they are describing exactly the same ket. And these so-called wave function in position space and wave function in momentum space, they are basically different representations of the same ket. So you just use either you choose your basis as eigenkets of position operator, and then you have this psi alpha of r wave function in real space. Or you can choose as your basis the eigenkets of the momentum operator. Then you have your wave function in the momentum basis or momentum space. Their interpretation is all the same as any other expansion coefficient. The expansion coefficients are always the probability that your observation will yield the corresponding eigenvalue of whatever it's multiplying. So psi alpha of r is multiplying an eigenket of position, so its absolute squared gives you the probability density that your particle will be in that ket, which is a particle at position r. Phi alpha of p represents multiplies the ket p. You see, just let me use the summation sign. Psi alpha of r, or this is phi alpha of p, p. They are equal to the same ket. Since I'm using different bases, the expansion coefficients are obviously different. But psi alpha of r squared gives me the probability that I will observe my particle in the ket r, and hence at the position r. And phi alpha p squared, absolute squared, gives me the probability that I will observe my particle in the ket p, and hence having momentum p. But nevertheless, these two kets, they are exactly equal to each other. And whichever basis you choose to represent your ket, you are talking about the same ket in the same Hilbert space. Which basis to use? Well, whichever one you like. But most of the time you will be guided with what do you want to measure. So if there's something particular that you would like to measure, then using the eigenkets of that quantity would most of the time simplify your life. So you tend to choose that basis. But whichever basis you choose, you should get exactly the same information, exactly the same result. Yes, questions? Now, there's an example in your book about some Gaussian wave functions. I do strongly suggest you to go over it. So there's an explicit calculation of momentum uncertainty in the momentum of that Gaussian state, the uncertainty in coordinate of that Gaussian state, etc. I strongly suggest you to go over it, but I think we will finish chapter 1 this lecture. Any questions? So see you on Monday.